Continuing on with class 22, we just did the polytropic processes, and we saw these equations, and we ended up getting this equation for work. And we talked about the importance of visualizing what these were on a PV diagram and a TS diagram, seeing what those polytropic process and the variations of them being isobaric, isothermal, isentropic, isochoric. Let's focus on the isothermal right here. Okay, so I have a bunch of stuff written down here, but let's walk through it instead. It makes a little bit more sense if you walk through it, in my opinion. All right, so we can't use the equations that we just found for work for an isothermal, right? We remember that we said for an isothermal, N is equal to 1, but we just found that the work is 1 minus N, so if that N is equal to 1, that thing blows up, and we know that's not true. So let's revisit the isothermal. And this might have actually been done in class 8 as well. So maybe look back at the videos for class 8 and see if you can find some of those. But anyway, for an isothermal process, N is equal to 1. Which is, so it's a variation of the polytropic process in that regard. So what we could say here is, once again, we could say that P is equal to a constant over volume, right? Now it doesn't have an exponent to it. So if you have the definition of work, we have the integral of constant, I keep doing that. It's going to be dV over V, which we know is going to be a constant times the natural log of V2 over V1, right? Because that should be V1 and V2 if you want it to be. Well, it is true. That's just true. So we can use as our constant, say, the constant. Let's pick either one we want, but we get P1 is equal to P1 V1, right? It's also equal to P2 V2. Right. So you could substitute in here and have the work between 1 and 2 is going to be equal to P1 V1 times the natural log of V2 over V1. Or, if you wanted to, you could say the work is going to be equal to P2 V2 natural log. Sorry, excuse me. Oh, I know why. All right, so we're still using ones. That's fine. But recognize that P1 V1 is equal to P2 V2. So let's see, I'm going to get this right. V2 over V1 is equal to, don't get me wrong here, P1 over P2. Yes. So therefore, you can also write this is P1 over P2. Right? So this guy right here, we're just substituting that right there. We also have the option, because PV equals MRT, right? So that's big V, not little v, so that M is still in there. We could say that the work between 1 and 2 is going to be M times R times T. And if this is isothermal, it doesn't matter. We don't have to put a number here. It doesn't have to be 1. It's going to be temperature all the time. And then that's just going to be logarithm of V2 over V1. Or, you can write another one right here. This is going to be MRT natural log of P1 over P2, right? So depending on the scenarios that you have, you might want to use some variation of those. And if you, these also kind of confirm some of the things that you might see in the constant temperature closed system here when it comes to work, right? And also in a constant temperature system, recognize that if the temperature doesn't change, the internal energy doesn't change. So Q is also equal to W, but you start to see, here's the variations that you start to see right there, right? That we just did and we just wrote down. So we're confirming those. And then I think, I think also in the last class, we also talked about entropy. But maybe we could, we're going to do that right down here. Okay. So for an isothermal process, we'll use this Gibbs equation. And so this is like, I can't remember which one. I would call this the first Gibbs equation, whichever one. This is the Gibbs equation. Gibbs-eq. And if it's an isothermal, if T is equal to constant, recognize, and I'm going to go where. Remember, we have du is equal to cv dt as a definition. So if dt is 0, so is u, du, so that goes to 0 right there. And recognize that that's q. So q is going to be equal to p dv. So we could go, or dq, I guess, or we could go del. Yeah, it's del q. And it's on a per mass basis. All of a sudden, we're starting to do per mass basis. It just seems like willy-nilly we're doing it. We can get q 1 to 2 is going to be equal to work 1 to 2. So some variety of P1, V1, and then natural log of V2 over V1. But you can see that there's other variations of there, etc. So that's just, I'm kind of reiterating, I guess, because I already said it a moment ago, that U is equal to 0, and therefore Q is equal to W. So, I don't know, that's 7 minutes worth of stuff. Is there anything? We got examples to go. So I'll make the next video's example, and we will make lots and lots of examples. Not as many as I'd like, though. More examples will almost be better. See you soon.